like the Chem 11. Okay. So at a given temperature and pressure, the volumes of gases react with one another in simple whole number ratios. So if I give you 1 liter of gas A, it's not going to be reacting with like 4.372 liters of gas B. It's going to be reacting with 2 liters of gas B or 3 liters of gas B. Yes? So you might have a 1-to-2 ratio or a 1-to-1 ratio, but you won't have like a 1 to 6.827 ratio, because that's not a simple whole number. So far, so good? Yes? Does that mean that in this volume, only so much of it, what's stopping the majority of giving gas? So if you have 1 volume hydrogen and like half volume chlorine, what's stopping you from having like just one volume hydrogen chloride and then half the volume? You can have like leftovers, but if you have hydrogen and you react it completely with chlorine, so there's no leftover hydrogen and no leftover chlorine, they will react in a 1-to-1 fashion. Does that make sense? So as long as we're not talking like having leftovers, they always react in simple whole numbers. Yep. So 1 volume of hydrogen and 1 volume of chloride gives us 2 volumes of hydrogen chloride. Now, if I was to ask you to please write the reaction for the reaction of hydrogen plus chlorine giving hydrogen chloride, could you do that? Go. Is it down here? Oh, look, it is. Then let's not bother. Okay, so we have hydrogen, H2. Oh, that's a highlighter, not a pen. We have H2 plus Cl2 gives, what kind of a reaction is this? If you have 2 elements that combine, that is synthesis, yes. And they combine and we get HCl. And in order to balance that, you of course need a 2 in front of the HCl. And the reason this works is because of what we talked about last day, is that equal volumes contain equal number of moles. It doesn't matter what the gas is, okay? So if you end up with twice as many particles, you will end up with twice the volume. Here's just another little picture, because I love pictures. I feel like they make it more meaningful. So if you have hydrogen gas, 2 hydrogens, I should really make this prettier because it's not very nice right now, and you add it to 1 oxygen, you will get 2 water. So you can have 3 volumes all together, giving you 2 volumes at the end. 3 liters is going to give you 2 liters. Does that make sense? Because you're starting with 3 different types of gas, or 3 particles, and you're ending with 2 particles. Here's more molecules, because like I said, I love particles, love diagrams. Okay, so you can see we have 1, 2, 3, 4, 5, 6 hydrogens, and we have 1, 2, 3 oxygen particles, and we end up with 1, 2, 3, 4, 5, 6 water molecules. Is good? Okay. So Avogadro's hypothesis just says that, and that's how they figured out that every time you have a certain volume, it doesn't matter what the gas is, it will always contain the same number of particles. Okay, so that's how they figured that out. And so here's my little balloon. So if you have a helium balloon, it's going to weigh 4 grams if it contains 1 mole of gas. If you have 1 mole of NH3, you guys know the name of NH3? Ammonia, yes. It is ammonia, not ammonium. Okay, ammonia is the neutral NH3. ammonium is NH4 with a plus sign. Okay, and that will weigh 15 grams because that's the molar mass, and oxygen, O2, will have a mass of 32 grams when this balloon contains 1 mole of O2. I think I'm just yammering on at this point about the same stuff that we've already covered. Like I'm just reading this and I'm like, yeah, okay. So the masses will be different, but the volumes will be the same because the particles weigh different amounts, but the number of particles is staying the same. You've memorized the number 22.4? Excellent. What temperature is that at? 0 degrees Celsius and 1 atmosphere. Do you know what 0, it says, don't look at it. Do you know what 0 degrees Celsius is in Kelvin? 273. Do you know how the scale works with Kelvin? So down here at absolute 0, this is negative 273 degrees Celsius, and it is 0 Kelvin. Yes? And if you go up 100 degrees, this would be minus 173 degrees Celsius, and this would be 100 Kelvin. Because the degrees are the same size as one another, they're just displaced by 273. So if we go all the way up to 0 degrees Celsius, that's going to be 273 Kelvin. Okay, it's actually 273.15, but 273 is close enough for now. Okay, alrighty. So using, oh my gosh, look, if we know that we have 22.4 liters per mole, what can we use that as? A conversion factor. Oh boy. So if I give you 2 moles of methane gas at STP, and it has to be at STP, otherwise we have to do some other calculations that are more complicated. Yes? Yes. You can, of course, get water, yes. And in fact, if you guys ever want to go to the washroom or get water, you can just go without asking me. Okay, you're big kids and you value your education, so I will trust you with that. You can just leave. If you wanted to walk out of here and just be like, I'm never going to attend this lesson again, you could do that. You probably would not do awesome in the course, but you know, that would be your choice. Okay? I would not say that to my grade 9s, for example. Okay. So once again, like everything else, just cancel your moles, find your liters, do the calculation. You need to do it backwards. If I give you liters, you put liters on the bottom, and the 22.4 always goes with the liters, not with the moles. That's the only mistake that people make, is sometimes they'll do things like they'll write 5.60 times, or sorry, liters, times 22.4 moles per liter, right? And that's the kind of mistake that I will see from time to time. And it's just a matter of going, oopsie, I put the 22.4 in the wrong place. Yes? It should be times 1 liter per 22 point, or, well, that's, yeah, no, yes. What am I doing? Now I'm getting it wrong. It is 1 mole per 22.4 liters. There we go. Okie dokie. I'm not going to give you time to do these right now. You can, if you are a super converter, you can just go do 11 and 12. Do you guys feel like you're super converters? Do you want to go do 11 and 12 right now? Go try 11 and 12. See how they go. Try 11 and 12.
I'm not super converted. You are. You can do it. You can do it, Samuel. All right, super converter. I get paid volunteer hours.
Okay, how are we gonna do it? Okay. How are we doing here?
What do you mean a little? I sent it to you during.
Press mode. Or change it back to flow.
I have a song I can teach you. You wanna learn a song?
I just take it.
All right, my friends, I'm going to interrupt you for a moment because even though you probably won't be tested on this specifically on the AP exam, it will behoove you to know your prefixes by heart, yes? And we know usually like centi. Like if I said centimeters, how would you convert that to meters? 1 meter is 100 centimeters, yes? There's a bunch of those that you already know, yes? Mega is 10 to the 6. So that means a megameter is a million meters, yes? Kilo is 10 to the 3. Now those are our big ones. Everything else is going to be negative. So deci is 10 to the -1, centi is 10 to the -2, milli is 10 to the -3, micro -6, nano is -9. Yes. Because because you know when you write numbers, you'll often go like this. Make it easy to read. That's why 3s, 6s, and 9s. Okay, so, and then these two, it's just because those are very commonly used, just because, you know, 1/10 and 1/100th are commonly used. The rest of them are all 3s and 6s and 9s. So there's a song that you can learn to remember these prefixes and their powers of 10. And we are going to learn it together, and then you can decide whether you want to keep learning the song or whether you want to make yourself what was it? A Quizlet instead to learn it. But I will teach you the song because it brings me joy, even if it tortures you, and that's what it's all about, right? All about bringing the teacher joy. Yes? Okay, so here we go. Mega, kilo, deci, centi, milli, micro, nano, mega, kilo, deci, centi, milli, micro, nano. So now we've got them in order from largest to smallest. Yes, so it goes mega, kilo, deci, centi, milli, micro, nano. Mega, kilo, deci, centi, milli, micro, nano. Everyone with me now? Mega, kilo, deci, centi, milli, micro, nano. Mega, kilo, deci, centi, milli, micro, nano. Now, once you get that, then remembering these ones, I mean, you can just be like, okay, I know there's 3s and 6s, and then there's a deci and then the deci's a tenth, and then the hundred. But there's also a part of the song that deals with those. Okay, so it goes mega, kilo, deci, centi, milli, micro, nano, 6, 3, 1, 2, 3, 6. 9 is for the nano. Mega, kilo, deci, centi, milli, micro, nano. 6, 3, 1, 2, 3, 6. 9 is for the nano. Mega, kilo, deci, centi, milli, micro, nano. 6, 3, 1, 2, 3, 6. 9 is for the nano. And then all you have to do is you have to be like, well, these are all negative, right? And these are all 10 to the whatever. Yes? Or you can make a Quizlet. Okay? So up to you what you choose to do with that information. Okay, I would actually like to go through number 12 with you guys just to make sure that the whole process makes sense, okay? So when I look at this, I look and I say, I am starting with hydrogen atoms. Yes? Eventually, I want to make my way to microliters of methane. All right? And if I go back to, where is it? Come on, mouse, do your thing. There we go. If we go back here, I could actually map my journey on here. I am starting with atoms of hydrogen. Yes? What should I be converting atoms of hydrogen into? Molecules. Molecules of H2. Or in fact, I'm starting with moles of, am I starting with moles of hydrogen atoms? Yeah, so I'm starting with moles of hydrogen atoms, and I am converting that into moles of CH4, not H2. Okay, so I'm all messed up. Yes, as usual. Okay, now that I'm at moles, right? Now I can convert to liters. And once I'm at liters, I can, of course, convert to any version of liter, kiloliter, microliter, whatever. Yes? So what that's going to look like then is 5.5. Come on, mouse, work. There we go. So we're going to go from 3.6 moles of hydrogen atoms to moles of CH4 to liters of CH4 to microliters of CH4. Does that make sense? So you would then say I have 3.6 moles of hydrogen atoms, because that's what I'm given. I need to cancel moles of hydrogen atoms and find moles of CH4, not atoms. What's the ratio there? There's 4 H atoms in every one molecule. Now those are gone and we are now here. Now we need to convert to liters. Fortunately, we are at STP, so life is good. So we're going to cancel our moles and find liters. Where does the 22.4 go, on the top or the bottom? Top, with the liters, 22.4 liters per 1 mole. And then we're going to go with the microliters. Now remember, what did we say about micro? Micro is 10 to the -6. The 10 to the, if you are using those prefixes and you're not just using your knowledge of what, like if you're saying like, oh yeah, I know that there's 10 to the 6 microliters in a liter, that's fine. But if you're using this, the 10 to the -6 actually replaces the micro. So up on the top, we have micro. On the bottom, instead of micro, we have 10 to the -6. Yes? You could do 10 to the 6 microliters per liter. And I don't care which way you do it as long as you get it correct. Yes? So whichever way makes the most sense to you, then you would go through and you would do your calculation. Make sure you can plug that into your calculator correctly and get the correct answer. Okay, because that's another step where you want to make sure you can plug everything in all right. The quiz? Yeah. You can do it tomorrow morning. Tomorrow morning, 8:35. Okay. Did you on your calculator get this number? Did I do it wrong? I did it wrong? Well, the sig figs are obviously wrong. But did you get the same number as I did? Yes? You did not? Okay, but do you know what you did wrong? Okay, that's cool then. So then at this point we would say how many is our smallest number of sig figs? So we now have 2.0 times 10 to the 7 microliters. Is good? Okay. Are we ready for 5.5b? Wait, oh, sorry. Yeah, no worries. Yes. That's right. Yep. Anytime you're converting in between metric units, like with the tens and whatevers, those are all infinite sig figs. Yep. Okay. And guess what? We can use this conversion factor, the 22.4 liters per mole. If we have the density of a gas, we can use it to convert to the molar mass of a gas. So if you actually like do an experiment and you measure the mass of a gas and you measure its volume and you find its density, you could use that to find its molar mass because you can do a conversion between liters and moles, right? So you do an experiment and you're like, I've measured the volume of this gas, I've stuck it on a scale, I've measured how much it weighs, now I know its density, you can find its molar mass. or vice versa. If I give you the molar mass, you can find the density. Okay, so here we have an example. Find the density at STP of natural gas methane. So the density of methane at STP. And you might look at that question and be like, You're like, how do I do that? Right? If you didn't know that you could find density from molar mass, that would be a problem, yes? So density is what's the unit on top of density? Grams per liter. And we could start with the grams per, I need something I know about CH4. I need a number attached to CH4 to do anything with it. You can find the molar mass of CH4, which is 12 plus 4, which is 16 grams per mole. So you can start with grams per mole, and then using the fact that it is at STP, you can take the moles and cancel them out and find the liters. And you want the liters to be on the bottom in the denominator, so it's good, that's where they are. Where does the 22.4 go? On the bottom with the liters, 22.4 liters per 1 mole. And we get 16 divided by 22.4 is, oh, why are you not behaving? Come on. 0.7143. And my units, the only thing I have left is grams per liter. Is that what I wanted? Yes. And that's not right, sig figs. I would want it to become 0.714 grams per liter. Is good? So the trick here is remembering, if I know molar mass of a gas, I can find density of a gas. If I know density of a gas, I can find molar mass of a gas, and you can use 22.4 liters. Will this work for liquids and solids? No, because they don't have a consistent molar volume, okay? All right, what's our next example? Here we go, we have a density of an unknown gas. So the density of an unknown gas is 4.22 grams per liter. And we would like to know its molar mass. Well, the nice thing is that we are told that this is at STP, which means we can use 22.4, okay? And we want to find molar mass. What is the unit of molar mass? Grams over moles. So we don't know what those things are. So we need to start with something, and we can start with our 4.22 grams per liter. All right, because our grams are in the right place. All we need to do is convert liters into moles. Okay, so we can do that by taking our molar volume. Liters have to go on the top, moles have to go on the bottom. Therefore, the 22.4 has to go on the top with the liters. 22.4 always goes with the liters. And we get, ooh, look, 4.22 times 22.4. It's almost like a palindrome, except it's not a palindrome. It's just backwards. 94. It's great, I'm laughing at my own jokes. Nobody else is laughing. Nobody gets an A+, none of you. Okay. 5 to 8. And when we cancel our units, all we are left with is grams per mole. And of course, we would have to take that to correct sig figs, so that would then become 94.5 grams per mole. Is good? Yes? Okay, can we cover another section today? Probably. Yeah, we could. Yeah. Okay, we're going to start on 5.7. Okay, 5.7. 5.7a on page 107. What happened to 5.6? Oh, that's a review. Okay. Where to go? All righty. So, my friends, we have the structural formula of ethane. What does the prefix eth mean? Two carbons. The suffix ane means that it is an alkane, which means that it is just carbon and hydrogen and just single bonds. Okay? Ane means it's an alkane. And alkanes are only carbon and hydrogen and only single bonds. So it's a hydrocarbon, yes. It's a very straightforward hydrocarbon. So when you see the ending ane, that means you have a singly bonded hydrocarbon. Ethane contains 2 carbons. How many bonds does carbon always form? Well, almost always. 4. There are exceptions. In carbon monoxide, it forms 3 bonds, but we'll get into that at some point in the future. So around each carbon has to be bonded to each other, of course, and on the remaining 3 bonds for each one, you have hydrogens. Okay? So the formula, that is the structural formula. Yes, structural formula. It contains 2 carbons and 6 hydrogens. That is our molecular formula. That's the name we give to that one. That's our molecular formula. There is a third type of formula, and that is called the empirical formula. Do you know the meaning of the word empirical? You'd think it had something to do with empire, but it actually doesn't. Yeah, it is from your own experience. It's from like experiments that you've done. Okay, so it's determined experimentally. Like so it's not something you've done in theory. You've actually physically done it in your real life. Okay. So we have the empirical formula, which implies that this thing should be able to be determined by experiment. And its empirical formula is CH3. Excuse me. So you guys are going to look at some of the other compounds and examples and see if you can spot the pattern between the molecular formula and the empirical formula. If you have spotted it, you can check with your partner and see if you spotted the same thing as they did. So compare these two. Like that, yes. Except for not exactly that. So how do the two relate to one another? What is the empirical formula? The empirical formula, you take the molecular formula and do what with it? You simplify it as much as possible. So it is the simplest whole number ratio, okay? The empirical formula is the simplest whole number ratio. So hopefully you figured this all out. What you are going to do at this point is, while I go and get a chemical, because we're going to do like a little demonstration experiment that's going to take a couple of days. Okay, but we've got the weekend, so that's good. While I go and grab that stuff, you are going to fill in the molecular formula and the empirical formula for these compounds. Okay? You don't have to have Tyler if you understood molecular and empirical. Okay? It's there just in case. Okay, are you guys ready for the demo experiment? Are you still ready? You're still ready. Take another minute. Finish it up. It's all good. Except for that the empirical formula doesn't matter what the real thing is. It's just the simplest one.
Does that mean there's a CH2 that exists?
No. The empirical formula doesn't actually matter. Okay. And this little experiment we're going to do is going to show you why we just do the simplest whole number ratio. During the I week?
My dad wants to know if we can plan to be away.
Sure. When is I week?
I think it's like 23rd of January.
I don't think so. Let me think on it for an evening and then get back to you. Is that okay?
Yeah.
Yeah, okay. No. I would have to look at the pages. You could probably figure it out. Whatever we did today, go to those pages and like do the questions. Yes? Okay, ladies and gentlemen, we have this little lab here. You are going to write down the procedure. I'm going to introduce you to some equipment. And it is going to introduce you to writing a procedure. Okay? So you need a piece of paper. It does not have to be beautiful paper. There is lots of free blank paper back here if you need some. Okay? some point, so make sure that you do it in something that can be torn out or whatever. So, this was when we were trying to timetable. This is what you get. You get pages and pages and pages of that. It's just scrap paper. These are just scrap paper. Hey, you guys know that when you do a lab, you're going to have a section called materials, yes? Okay, so you're going to write materials, and then I'm going to kind of do this, and you're just going to ask me questions. All right? Now, when you write a procedure, how does one generally write it? In steps. So do we number those steps? Yes, we do. What voice do we use? Command form, okay? Because you don't want to be like, and now, young children, you are going to, no, it's just like, do this, do that. It's very like prescriptive, okay? So, feel free to ask questions. Oh, what is that? It is 1 molar ammonium chloride, 1.0 molar ammonium chloride. Yes? Oh, what's the name of the lab? Let's call it lab, shall we? We'll figure out a title once we're done. Okay? Once we've seen what happens, you can figure out what the title will be. Okay, we'll work on writing a good title afterwards. All right. This is, shall I write it down for you? I could do that. 1.0 molar. What do I write for molar? Big M or little m? Big M. Molar ammonium chloride. Okay. What's that? It is a crucible. Have you heard of a crucible? It's made of ceramic, so it can withstand very high heat. Okay? This is a crucible. Steel wool. Steel wool. I'm scaling across. Oh, very nice. I love a really bad pun. I would have to. My husband throws them around all the time. Oh my God. Can't take him anywhere. Always telling bad jokes. King of the dad joke. Oh my God. All right. Oh, no, no, I messed up. What am I doing? So now we're on procedure. Although I'm actually going to do it again because I think I've moved it and I've unzeroed it. So I'm going to zero it. Oh yeah. What do you call that kind of scale? A weighing scale? Balance, a balance. We call them balances. You could also call it an analytical balance, which is apparently what it says on the box, but I've always called it an electronic balance, so that's fine. And in addition to our materials and a procedure, we are going to have our data and observations. And everyone should write down Jeremy Tam. No, his quiz was up there. Yes. No. Because you don't even know what we're doing yet. So we're kind of going a little bit. It's going to be a bit of a different lab. Okay? No, you're not writing plug-in balance. You don't write down things that are quite obvious. Okay? So do you have your first procedure step? Yes? Do you have any data or observations yet? No. I do. What do I see? 22.37 grams. Twenty-two point three. I'm not telling you yet. We'll tell you later, okay? Actually, it says 22.34. 22.34 grams. Should I write my observation like that? What am I missing? Information. What am I missing about this? Units. What else am I missing? Context. What the heck is this number? Is that my eraser? I don't know. So what should I put over here? Is it the weight of the crucible? Mass. Because weight is different from mass. The mass of this crucible would be the same whether we are here or on the moon, right? Because the force of gravity does not affect mass. Mass is the amount of matter in there, but it would affect the weight. So it's not the weight. This is the mass of the crucible. Okay. Okay. Did I tear it? No, I did not. Oh, what's the mass of the steel wool in the crucible? It is 23.73 grams. So I did not press tear in between, so that is the mass of what? The crucible and the steel wool. tongs. Crucible tongs. And because we don't have time today, I'm not going to actually pass around the plain steel wool for you to make observations on. I will pass it around next class. Okay? Crucible tongs. Crucible tongs. They can be used if you need to hold a crucible like this. Okay? Or like this, depending on the context, right? So that's how you could use them. We're not going to use them for that today, though. We're done for today. It's a multi-day lab. How long did I don't know, I just kind of dunked it and smushed it so it sort of had stuff in it. Submerge the steel wool, make sure it's kind of like, you know, it's a bit like a sponge. Squishy, squishy. Put it back in.
5 seconds.
Sounds good to me. All right, so homework. Let's find this, what this is for you. So you need to do as much of this as you need to in order to feel like you are happy and comfortable with it and could do it under any circumstances, yes? And where have I put my book? Bloody hell. Okay. Oh, there it is. Yay. Okay.
Well, no, I was gonna say dip,
I said did and dip, dip, and then dip.
Okie dokie. This demonstration lab is leading up to you guys doing your own lab that is based on similar principles. Okay? Pages 90 to 91, odd numbers, and then 93 to 94, all. Oh, oh yeah, people have done it already. Oh yeah, they're like, oh, I want to come in tomorrow and do it, and I'm like, oh yeah.
Can I still do it?
Oh, absolutely, yes.
Also, how does it work? Is it like
I take whichever one is better because I don't want to deal with
Is
it.
it like similar, like same amount of questions?
It's similar questions, just the numbers and compounds are different.
Yeah.
Yeah.
So can I come in tomorrow?
Yeah.
In the
Yeah.
morning? Flex?
Sure. Yeah, flex is good. Yeah. Ladies and gentlemen, one last thing. 5, 4, 3, 2, 1. You want to come and redo your quiz? Come and do it anytime during flex. If you cannot make it during flex, let me know. If you don't want to redo your quiz, then don't worry about what I just said. Have a great evening. I'll see you tomorrow. When you're going between moles and moles, so if I already give you moles and you want moles, but if I give you atoms, you will go to molecules. Like if I give you not moles of them, just number of them. So these ones will be big numbers. These will be like times 10 to the blah, blah, blah. These will be like normal numbers like 5.8. Yeah? Yeah.
I was just confused on number 12.
We can take a look at that one if you want to. Yeah. Hi.
I worry about making love to like
Yes. Oh, don't worry about making it look too just legible. Legible.
are we handling that?
We'll be filling it in, but it does not need to be beautiful, but it needs to be legible. Okay? So don't stress about making it beautiful. Hello.
Can we take the tech out?
I have a staff meeting.
Okay, never mind.
Yeah. Sorry, other than if it weren't a staff meeting, I would say yeah, but yeah. Hi.
Do you replace the better one?
Yeah, whichever one's better.
Okay, so if it's worse,
Then it doesn't count. Okay. I will not be here at lunch. I eat lunch at lunch. So either are you doing something during flex time? Do you have a class or something? What is flex is at 8:35. 9:05. I can come in a little earlier though if you need me to. Like if you're like I need more than half an hour, I can make arrangements. I don't know. I do know that Aaron rewrote it this morning and she started at about 8:40 and she finished by the time it was time to go. A couple guys came in late at 8:45 and they didn't finish until after the bell for first class again. So if you wanted to be here at like 8:30 tomorrow, I'm pretty sure you can finish it in time.
it's okay. I'll call around 8:45.
8:35? Perfect. Sounds good. Hello.
So you would call this ammonium chloride solution.
Yes. Beautiful. Yeah, for sure.
I haven't, like, despite my trip French,
With Miss Leave It.
unlucky, isn't it? Unlucky.
I found it.
You found it? I literally put it under there.
You found it.
I mean, technically, good life. I was just until no, for real. Dude, he gave it to me as a birthday gift, man. You want some? Do you want one or two? Yeah. Dude, I am cash flow. Cash flow. Thank you.
Thank you. See you later. Okay, where did I put? Oh, there.
Thanks, Miss Burns.
You're welcome, Daniel.
on the office.